Alrighty, most missed quadratics, phase 3. This problem you might like because it actually has to do with the real life stuff instead of just a bunch of things that we make up as mathematicians. So the height of a ball thrown is represented by the function h of t equals negative 16t squared minus 32t plus 1584. It's asking us to give a reasonable domain and range, and this gives a general question: how long does the ball take to hit the ground? So this is a graphing calculator problem. That's all it is. You need to go into your whatever graphing calculator you're using, pretend like we're using the TI formatted calculators. So y equals menu, you need to make this a function of x. Because in the graphing calculators, everything is in terms of y and x. Minus 32x plus 1584. Now, I'm not even going to bother looking at the graph yet, because I don't know what kind of values this function is going to take on. So I need to study the table. If you're in a graphing calculator, go straight to your table. Here's the thing. Remember that x represents time in seconds, and y represents the height of whatever this is that's being thrown. So I'm going to start looking at x values at 0, because it wouldn't make sense to look at negative values since there is no such thing as negative time. This is coming straight from the calculator. When x is 0, y is 1584, 1, 1536. Anyway, this continues on in this fashion until finally you reach a critical value, a root. You do reach a 0 for this function at x equals 9. Now, why is that important? Well, if we were going to study a graph of this function, think about this. Y represents height, and x represents time. So, at time 0, we have this point, 0, 1584. As time is progressing from the table, we can tell it's getting lower and lower to the ground until 9 seconds pass and we're at height 0. We do have this point 90. So that tells me a few things. It does tell me, for one, this object was thrown from a height. It was thrown off of a cliff or off of a building or something, because at time 0 it's already above the ground. So it's not something that was launched from the ground. Reasonable domain and range says, where do we care to look at this function? For example, I talked earlier about it doesn't really matter what the negative values for x are, because we're talking about time, and negative seconds don't exist. So a reasonable domain and range is just saying, how can we restrict our view of this function to values which make sense? So think about it. The entire event took 9 seconds. So from here to here on the graph, as the x value started at 0, the maximum x value we cared to look at was 9. In this case, they're using the variable t, so let's put it in terms of t. We'll say t has to be a value between 0 and 9, and it can include 0 and 9 because things are happening at those points in time. Range deals with height, so remind yourself, domain is time, range is your height. And instead of using y, I'm going to just use h of t. And we need to establish a minimum and a maximum value. So the lowest y value on the function that we care to look at is 0, since the object doesn't go underground. And the highest value is actually right here at 0, which is 1584. This function actually does have a higher value before 0. It has a value of 1600 at x equals -1. However, it does not matter because x equals -1 is not part of the domain. There is no domain value for when time is -1. There's no matching range value. So The highest this object ever is 1584. That's in feet. And the lowest is 0. That's the reasonable range of the function. And what's cool about that is reasonable domain and range go hand in hand with how do I set my calculator window settings. So if you want a good view of this function in your TI calculator, you have to hit the window button, set X minimum and X maximum as your reasonable domain, and set Y minimum and Y maximum as your reasonable range values. So think about it like this, it's going left to right for X values. Minimum you should set 0 and the maximum 9. Now that doesn't give us any wiggle room, so normally I like to set it maybe to -1, maybe increase this by a couple. And then out of our Y values, minimum should be 0, maximum should be 1584. And again, you might want to increase that maximum value just so you can get the entire view of your graph in your window. So that's how domain and range are connected to the window settings. And if you ever want to go back to the standard -10 to +10, hit the zoom button and select 6. I believe it's called zoom standard. So B says how long does it take the ball to hit the ground. You look at this root right here, which is at time equals 9, and just judging based on the graph and the table, it takes 9 seconds. That's when the height is back at 0. The last problem I wanted to address, I've switched. So, when approaching this problem, we have to think about quadratic functions. They are always going to be parabolas, no matter what they are. So, there's actually only 3 possible things that can happen when you're looking at a parabola and the x and y axes. The parabola could touch the x-axis at 2 different points. That is a quadratic function which has 2 real roots. A parabola could also touch at exactly 1 point, or if you want to get technical, which I always do, we would say that that parabola is tangent to the x-axis. That means it has 1 real root. Okay, just logically thinking about this, the only other thing that could possibly happen is if your vertex is way up here and you're opening upwards, or it could be that your vertex is down here and you're opening downwards. In either case, it never crosses the x-axis. Some quadratics never touch the x-axis. When that occurs, this function has 2 distinct imaginary, or what we sometimes call complex roots. If you test out this function in the graphing calculator, it looks something like this. That would be the 3rd case there, meaning it never crosses the x-axis, so it must have 2 imaginary and complex roots. The trick answer is D, no roots, because you would think if it doesn't ever cross the x-axis, it must not have any roots. Not true. Every quadratic has roots, sometimes you just can't see them. That's why they're called imaginary. Well, that's one way you could think of the word imaginary. So no roots is, as I like to call it, it's a ruse. It's a trick. Don't fall for it. Alrighty.